In this video, we're going to study intermolecular forces and polarity, and that'll include an explanation of dielectric strength, dipole moment, solubility, and types of intermolecular forces. Now, truth be told, I don't personally find this a particularly exciting area of chemistry, but it is fairly straightforward and it is very useful. It explains a lot about the physical properties of the elements and the compounds, so it's worth the time spent. Let's get started. So what is the importance of molecular polarity? The polarity of molecules strongly influences their melting points, their boiling points, and their solubility. Let's define molecular polarity, and we'll do it in the first case as a negative. So a covalent bond is nonpolar when it joins atoms of similar electronegativity, like H2 and hydrogen. Here's hydrogen on the periodic table. Its electronegativity is 2.1, but since it's bonded to itself, it's irrelevant. The electrons between the atoms will be shared equally. So if we do a calculation of difference in electronegativity, it works out to be 0, and this is classed as a nonpolar covalent bond. If we were trying to visualize a hydrogen molecule, we notice that the shared pair of electrons is represented by a line. But the electrons are not confined to this space. We know, in fact, that they're randomly moving at approximately 1/10 the speed of light in this cloud. And the cloud is symmetrical because the electrons are shared equally. Now, a covalent bond is polar when it joins atoms of different electronegativity, like in HCl. The electronegativity of chlorine is 3, and of course hydrogen is 2.1. The difference is 0.9, and that's classed as a polar covalent bond. And therefore the atoms share the bonding electrons, unequally. If we were to visualize an HCl molecule, this shared pair of electrons, just the bonded pair, is actually moving around, and it spends most of its time near the more electronegative atom, making chlorine slightly, partially, or delta negative is the symbol we use for that. The electrons only occasionally visit the hydrogen, leaving the hydrogen as slightly, partially, or delta positive. Now, in a diatomic molecule, such as HCl, the polar bond will cause the whole molecule to be polar since there is only one bond in it. Take a look at this illustration. It's an electric circuit diagram of a parallel plate capacitor. So we have two parallel metal plates. One side is connected to the negative terminal of a DC power supply and the other one to the positive terminal. You can think of this as a DC battery. The plate connected to the negative terminal will have electrons in excess on it, therefore it's negatively charged. The plate connected to the positive terminal will be electron deficient and it has a positive charge. So we have in effect an external electric field. Now, molecules with their own molecular polarity, such as HCl, when they are placed between the plates of a parallel plate capacitor, they will align themselves or orient themselves such that the slightly positive end will be pointing towards the negative plate and the slightly negative end of the molecule will be pointing towards the positive plate. So I want to look at how polarity is actually measured. The magnitude of polarity of a molecule is reported as the dielectric constant. And dielectric just means electrically insulating. Take a look at the illustration below. In figure A, we have a parallel plate capacitor with a vacuum or nothing between the plates. We're applying an EMF of 1.5 volts. And that sets up an electric field. We'll call it E sub 0. In figure B, we've removed the power supply and placed a voltmeter in its place. Now, voltmeters can measure voltage without allowing current to flow. And it turns out that the voltage is unchanged because capacitors store electric charge for long periods of time. In figure C, we take a polar molecule such as HCl and place it between the plates. And A polar molecule will set up its own electric field. This will be E1 opposite to the external electric field E sub 0, in effect reducing the overall electric field between the plates. So the net electric field will be the initial one, E sub 0, minus E1. In the lab, we'd simply see the voltage has reduced from 1.5 volts to some lower value, 1.15 in this case. That reduction is caused by the polar molecules between the parallel plates. So the more polar the molecule, the greater is the voltage reduction across the external electric field. Interestingly, even nonpolar molecules like hydrogen and oxygen will reduce the external electric field somewhat. And that's because weak dipoles are induced in the nonpolar molecules and they oppose the external electric field. And we'll be explaining more about induced dipoles later in this lesson. Here's the calculation. V sub 0, voltage measured with vacuum between the plates, is divided by the voltage measured with some substance between the plates. It gives us a value which we give the symbol K to the dielectric constant, and this is proportional to the polarity of a substance. The dielectric constant is dimensionless, that is, it's unitless, because the units of voltage will cancel from both numerator and denominator, and it simply indicates the magnitude of polarity of a molecule. So polar molecules are good dielectrics, that is, they are good electrical insulators. Now, hydrogen bonded substances, and we'll talk more about hydrogen bonding later in this lesson. Examples include water, hydrogen fluoride, and ammonia. They are especially good electrical insulators, and good solvents. Will explain also why that is later. Please take a look at this table. I've listed some common solvents in order of increasing polarity, increasing dielectric constant. At the bottom of the list we have hydrocarbons like methane, ethane, propane, butane, the alkane series. They all typically have a dielectric constant of 2. That's because they're made of atoms with very little difference in their electronegativity values, and therefore they are nonpolar. Here's water way up on the list, a very polar molecule with a dielectric constant of 81, which simply means that the voltage in a vacuum is about 81 times greater than in the case with water present. So water greatly reduces the net electric field because it's so polar. What's the effect of this? What's the application? Well, take a look at the melting point and boiling point trends. You'll see that in general, as the dielectric constant increases, so does the melting point, so does the boiling point. They become higher and higher melting and boiling because they're being held together more strongly by the polarity of the molecule. Now, one other factor that affects melting points and boiling points is molar mass. So melting point and boiling point directly relate to molar mass. All else being equal, larger molecules with greater surface area are held together more strongly than small molecules of similar polarity. So let's look at that. For example, here I have dimethyl ether and acetone, both with dielectric constants of 21, so similar polarity. However, acetone has a considerably higher melting and boiling point than does dimethyl ether, and that's because of its higher molar mass. Note also, please, that as we add atoms with greater electronegativity, there is a greater difference in electronegativity between atoms being bonded, and this gives rise to greater polarity, greater dielectric constants. Let's consider molecular polarity and solubility. Now, water is often referred to as the universal solvent in that it dissolves so many substances, but in truth it's not really a universal solvent. Water dissolves many ionic compounds like table salt and many polar compounds like sugar, but relatively few nonpolar compounds like the hydrocarbons, gasoline for example. Since water has such a high dielectric strength, 81, we know it's a good electrical insulator. and strong dielectrics reduce solute-solute attractive forces. And I'll try and illustrate that here. This is potassium chloride solid salt in a crystal lattice. When placed in water, it dissolves and the ions are separated and surrounded by water molecules. The small, highly polar water molecules will interject or squeeze themselves between the ions in the solid and in the liquid. Note that the negative pole of the water molecule, that's the oxygen atoms, are pointing towards and attracted to the potassium cations. Notice that the positive pole, that is the hydrogens of water, are pointing towards and attracting the chloride anion. In this way, water molecules effectively insulate these ions from each other and make it easier for the solute to pass from the solid state into solution, that is, easier to dissolve. To get some appreciation of the magnitude of this force, consider that the melting point of potassium chloride is 770 degrees C, and melting a salt won't even separate the charges. If I want to truly separate the ions, I'd have to bring it to the boiling point. In the case of KCl, that's 1420 degrees C. I'd have to heat this salt to over 1,000 degrees to separate cations and anions. Yet water will separate the potassium and chloride ions from each other at room temperature when it dissolves. Pretty remarkable. Water of hydration. Many polyvalent ions, such as copper-2, will dissolve exothermically in water, forming what are called hydrated ions. This one is named tetra aqua copper-2 ion. In many cases, the water molecules of hydration are strongly held, and they will accompany the cations right out of solution when the solids are crystallized. And so we wind up with these hydrated compounds, copper-2 sulfate pentahydrate. Here's a picture of it here, beautiful blue crystal. Also, we find compounds like magnesium chloride hexahydrate. This will be ferrous nitrate hexahydrate. This will be ferric sulfate nonahydrate. Another example is potassium aluminum sulfate dodecahydrate, commonly called alum, which is used for clarification of potable water. The attraction between anions and water is not nearly as important as the attraction between cations and water, and that's because cations are generally smaller. They've lost electrons, and their charge, therefore, is highly concentrated. They have what we would call high charge density. The non-hydrated water can be removed from a solution of copper-2 sulfate or any polyvalent ion for that matter by drying at 100 degrees C, leaving copper-2 sulfate pentahydrate crystals. If you want to remove the water of hydration and obtain anhydrous copper-2 sulfate, one would have to heat to 560 degrees Celsius, which indicates that these hydrated water molecules are held quite strongly. We've talked about solute-solvent interactions. Let's talk about some solvent-solvent interactions. Liquids having similar dielectric constants, for example, water 81 and ethanol 24, are likely to be miscible. I'm sure you're aware that ethanol dissolves in water in all proportions, and that's what miscible means. Liquids with very different K values, like water and methane or hexane or gasoline, all around 2, would normally be immiscible, that is, insoluble in each other. Then take a solvent like diethyl ether, whose dielectric constant is intermediate between, say, a non-soluble hydrocarbon and ethanol. Diethyl ether is 4.3. It will have an intermediate or modest solubility. Turns out this is 7 grams per 100 mils. The general rule is like dissolves like, and the dielectric constant can be used to roughly predict the solubility of various solvent and solute combinations. Another method of expressing molecular polarity is called the dipole moment, and like dielectric strength, the dipole moment is determined by measuring the voltage changes between electrically charged plates of a parallel plate capacitor when various substances are placed between the plates. But the results are expressed differently in the case of dipole moments. So here again is a representation of an electron cloud around a polar bond. We have a delta plus end and we have a delta minus end. These are two poles and hence they're referred to as a dipole. Now the size of the dipole is quantified by the dipole moment. The symbol is mu here, and it's defined as the product of the amount of charge that is separated, Q, times the distance over which the charges are separated, D. Now the charge of one electron is 1.6 times 10 to the minus 19 coulombs, and coulombs is a unit used for charge in calculating dipole moment. The distance between charges in a polar molecule is very small, in the order of 10 to the minus 10 meters. When we multiply Q times D, we're going to get values that are very small, in the order of 10 to the minus 29 coulomb meters. And so we use a unit called a debye, which is defined as 3 1/3 times 10 to the minus 30th coulomb meters. By using this unit of polarity, it'll give us dipole moments that fall between 0 and about 15 for virtually all molecules. And that's a very handy set of values to work with. Here's a brief table of some dipole moments of some polar bonds. Starting with the least polar hydrogen iodide, the difference in electronegativity is small, and so is the dipole moment. As we move towards more polar bonds like hydrogen fluoride, we have large differences of electronegativity. Likewise, the dipole moment and polarity are seen to increase. In a molecule with only one covalent bond, like HCl, 1.1 debye, the dipole moment of the bond is going to be the same as the dipole moment of the whole molecule. But the dipole moment of a molecule with more than one covalent bond would have to be the vector sum of all the dipoles in the molecule. I have a brief table here showing some dipole moments of various molecules. Of course, we would expect chlorine to have a dipole moment of 0 since it's completely nonpolar. And we'll look at some of these structures in just a moment. I want to point out too that water, which we know is quite polar, has a value of 1.85 debye. And for comparison purposes, here is an ionic compound where there's greater charge separation than in these polar covalent compounds, and we see a pretty high value, 9.0 debye for sodium chloride. So here's some structures. What I'd like us to do is estimate the net dipoles, which I'm showing here. And to do this, we're going to mentally, not mathematically, but simply mentally combine individual bond dipoles. We'll have to keep in mind at some point that the non-bonded pairs or lone pairs of electrons will also contribute to dipole moments because they represent a charge separation where the nucleus would be thought of as delta plus and the delta minus part is the pair of electrons. And we will only do this in a very loose fashion, so the best we can do is roughly estimate. So in the case of formaldehyde, we can see it has a dipole moment of 2.3 debye, so it has some polarity, contributed by, well, 3 dipoles here. The difference in electronegativity between carbon and hydrogen is pretty small, 0.4, so I draw very small dipoles pointing in the direction of the more electronegative atom, the carbon. That means that this end of the dipole is negative and this is positive. And in the carbon to oxygen bond, I have a bigger difference, 3.5 minus 2.5 is 1.0. This would then be a bigger dipole. If I added all 3 of these vectors together, head to tail, I would come up with a net dipole pointing in this direction. And I would say, okay, formaldehyde is likely polar. I'd be correct. In fact, it's miscible in water. Take a look at carbon tetrachloride. Notice that the dipole moment is 0. It does have some polar bonds in it. If we look at chlorine is 3.0, carbon's 2.5, and we can draw some dipoles in the direction of the more electronegative atom in each case. To have a dipole moment of 0, these vectors must all combine to add to 0. Now, looking at a two-dimensional drawing, it's pretty difficult to say that that's true, but if we look at instead a three-dimensional drawing, we could probably convince ourselves that these four dipoles combined head to tail in 3 dimensions do in fact return to the origin. The net dipole is 0. Look next, please, at carbon dioxide. Also has a dipole moment of 0. It does have some pretty polar bonds. The carbon to oxygen bond, 3.5 minus 2.5, has a difference of 1 in electronegativity. So there are two dipoles, equal but opposite in direction, and they will simply cancel. And we have no net dipole. Carbon dioxide has very low solubility in water because it's nonpolar. Next we have methyl chloride, which has some significant polarity. Again, the hydrogen to carbon bonds will have very small dipoles pointing in this direction, and the carbon to chlorine bond will have another dipole pointing in a similar direction. And if we combine all four of these dipoles together, we would get a net dipole indicating that yes, this has some polarity. How about chloroform or trichloromethane? It has some polarity. Let's put in some dipoles and take a look at that. We have a carbon to hydrogen dipole pointing toward the more electronegative atom. We'll have 3 of these dipoles from carbon to chlorine, again pointing toward the more electronegative atom. If we combine these vectors together, head to tail, we'd get a net dipole pointing in this direction. We could at least conclude that there's some polarity to this molecule. Next we have acetonitrile, very high dipole moment, 3.9 dBs. Well, let's take a look. Nitrogen has the same electronegativity value as chlorine. They're both 3.0. And carbon is 2.5, so there's a small dipole pointing towards the nitrogen. And there'll be another dipole pointing towards the electrons, the non-bonded pair of electrons. So if I were to combine these two dipoles together, I could say there's a net dipole in this direction that makes acetonitrile fairly polar, and in fact, acetonitrile is very polar. It's miscible in water. Next we have ammonia, also miscible in water. Let's add in its dipoles. We have the nitrogen to hydrogen bond. Nitrogen 3.0, hydrogen 2.1. The difference is 0.9. Some pretty big dipoles pointing in the direction of the nitrogen. Again, we could draw another dipole from nitrogen toward the pair of electrons in this direction. If I combine these head to tail, I'll get a single dipole, a net dipole in this direction. This tells me that the nitrogen is delta negative and this end of the molecule is delta positive. Here next we have water, which we know is quite polar. The value is 1.9 dBs. The oxygen to hydrogen bond is quite polar, 3.5 minus 2.1. The difference is 1.4, so some pretty big dipoles pointing from hydrogen toward oxygen. And then we can add a couple of dipoles for the pairs of electrons away from the oxygen. Combining all 4 of these together gives us a net value in this direction. The oxygen is delta negative. The hydrogens are delta plus. It is a polar molecule with a dipole moment of 1.9 dBs. And finally, we have acetone, and it's pretty polar by the look of the dipole moment magnitude, 2.9 dBs. Well, again, we have the carbon to oxygen bond. That's 3.5 minus 2.5. We have a dipole in this direction. We could draw 2 more dipole arrows representing the electron nucleus separation of charge. Combining these 3 together, we get a net dipole in this direction. And in fact, acetone is also miscible in water. So we're not trying to be mathematical. It was just to get a rough sense of predicting polarity and a rough sense of charge. The contribution of lone pairs we've seen helps explain the large dipoles in some of these molecules like acetonitrile and acetone. I want to point out one more item to you here. This is nitrogen trifluoride. Notice that its dipole moment is very small, 0.24 dBs, whereas over here we had ammonia and its value was 1.5 dBs. Why such a difference? These nitrogen to fluorine bonds are quite polar. Fluorine is 4.0, nitrogen 3.0. They're one difference in 1 electronegativity, and then we have our nitrogen to non-bonded pair electron bond. Well, let's add those dipoles in. Again, we have a dipole toward the electrons away from the nitrogen, Then we'll have dipoles from nitrogen to fluorine, but notice that these dipoles point away from the nitrogen rather than towards it in the case of ammonia. And so if we combine these dipoles together, we get a small dipole, 0.24 divised, actually facing the opposite direction. So the negative end of this molecule is towards the fluorines, and the positive end is towards the nitrogen. Two types of molecular forces. Intramolecular literally means within the molecule. Just like the word intramural sports refer to sports that are played within the walls of a school. In the case of an HCl molecule, the intramolecular distance is the distance between the two nuclei, and the intramolecular force is that force of attraction holding the hydrogen and chlorine nuclei together, namely the electrons. Intermolecular literally means between. Inter is between molecules. In the word intervarsity, these are sports that are played between different varsities or different schools. And in a sample of hydrogen chloride, the intermolecular distance is the distance between two molecules, and the intermolecular force is that force of attraction between the dipoles of two different molecules. Both the bonding, that is the intramolecular forces, and the intermolecular forces arise from the same cause, both from electrostatic attraction of opposite charges. In the case of ionic compounds like sodium chloride, oppositely charged cations and anions are attracted. In covalent compounds like HCl, the intramolecular attraction occurs between the atomic nuclei and the shared electron pairs, whereas intermolecular attraction occurs between adjacent molecules. Now, without intermolecular forces, substances would not hold together as liquids or solids. All substances would be non-condensable gases. These two types of force differ in magnitude. This is Coulomb's law. According to Coulomb's law, the larger the charges, Q1 and Q2, and the smaller the distance between them are, the greater will be the electrostatic force of attraction between two charges. Now, bonding forces, that is intramolecular forces, are relatively strong since they involve higher charges that are closer together. And intermolecular forces are relatively weak since they involve lower charges that are farther apart. Let's get an overview of both intra and intermolecular forces. First of all, intramolecular forces include ionic compounds, covalent compounds, and metals. In the case of ionic compounds such as sodium chloride, we have cations and anions attracting each other. In most cases, this is the strongest form of intramolecular force, from 100 to 1000 kcals per mole. Next on the list we have covalent intramolecular forces, as occur in covalent molecules like hydrogen or HCl, in which nuclei are attracted to the shared electron pairs, the bonding electrons. And the bond strength ranges from 35 to 250 kcals per mole. And we have metals are held together by intramolecular forces, in which the cations are attracted to delocalized seas of electrons that are free to move through the solid in the range of 18 to 240 kcals per mole, for example, iron metal. We really want to spend most of our time looking at the intermolecular forces. And there are 6 different kinds we're going to describe. The strongest of these is termed an ion dipole force of attraction, as we might see when sodium ion is dissolved in water. Sodium being the cation, water providing us with this dipole. So the negative end of the dipole here, oxygen, is attracted to the cation. This is in the range of 10 to 140 kcals per mole. It's referred to as an ion dipole attraction. We also have dipole attraction, in which two polar molecules are attracted to each other. So here I have iodine monochloride attracting iodine monochloride. Chlorine is more electronegative, so that's the negative end. Iodine is less electronegative, so that's the positive end. Those ends will attract each other in what is called a dipole-to-dipole intermolecular force of attraction. This is in the range of 1 to 6 kcals per mole. Hydrogen bonding is actually a special case of dipole-dipole attraction. It occurs when we have fluorine, oxygen, or nitrogen. In this case I have oxygen bonded to hydrogen, and that hydrogen is attracted to another fluorine, oxygen, or nitrogen. Water is one example. So this is the strongest form of dipole-dipole interaction, and it ranges from 2.5 up to 10 kcals per mole. And I'll give more detail on this on subsequent slides. Next, we're looking at an ion-induced dipole intermolecular force of attraction. So for example, if I have a chloride ion next to a bromine nonpolar molecule. Now I've tried to illustrate the nonpolar nature of bromine by this symmetric white circle of an electron cloud, which is the way it is before it is brought in proximity to chloride. But when it's brought close to chlorine, this electron cloud is distorted, and in fact an induced dipole is created in the bromine molecule, in which the end of the bromine molecule closest to the negative charge becomes delta plus, and the end of the bromine molecule farthest from the chloride becomes delta minus as electrons move away from it. So this dipole is only created or induced when in proximity to a charge. It's referred to as an ion-induced dipole force of intermolecular attraction, ranging from 0.7 to 4 kcals per mole. Well, instead of inducing a dipole with an ion, it can also be induced with another dipole. So for example, if we had HCl in proximity to a nonpolar molecule, chlorine, like bromine. Now chlorine is nonpolar, as illustrated by this symmetric white cloud of electrons, but when brought in proximity to this permanent dipole, HCl, then the electron cloud in the chlorine is distorted and a dipole is induced in the chlorine molecule. The end of the chlorine molecule that's closest to the chloride in HCl becomes delta plus. The end of the chlorine molecule that is farthest from the chloride becomes delta minus, as electrons in chlorine tend to flee away from it. This is called a dipole, induced dipole, intermolecular attraction. Strength ranges from 0.5 to 2.5 kcals per mole. And finally, the weakest form of intermolecular force is London dispersion forces. So here I have two nonpolar atoms or molecules. In this case, they're neon atoms. And they would have, as illustrated by the white symmetrical circles, they would have symmetric electron clouds. But when brought in proximity to each other, they distort each other. Each induces a dipole in the neighbor. And that's in the range of 0.01 to 1 kcals per mole. This is sometimes referred to as an induced dipole interaction. And I'll explain in more detail on subsequent slides. Let's look at an ion-dipole intermolecular force of attraction. So when an ion, such as chloride or sodium, and a nearby polar molecule, such as water, attract each other, this is called an ion-dipole attraction. Again, an ion-dipole attraction. An important example takes place when an ionic compound dissolves in water. The ions are separated because the attractions between the ions and the oppositely charged poles of the water molecule, that is, the ions are attracted by the oppositely charged poles of the water molecule, and these overcome the attractions of the ions to each other. For example, sodium chloride in water produces hydrated sodium ions, as we see here, and hydrated chloride anions here. Ions bonded to several water molecules are said to be hydrated, and any energy released in the process is called the heat of hydration. For solvents in general, not just water, but any solvent, ions are said to be solvated by the solvent, and the free energy change is called the heat of solvation. Now, according to the Arrhenius theory of acids and bases, an acid is a substance that contains hydrogen and dissolves in water to produce hydronium ion, H3O+. So HCl is an example of an Arrhenius acid. It dissociates completely in water, producing hydrated hydrogen ions and hydrated chloride anions. Now, we commonly write hydronium ion as H3O+. We might illustrate it this way, showing hydrogen ion being hydrated by a water molecule. But it is thought that the X in this equation for the number of water molecules is about 4. So we should more correctly draw hydronium as this structure, but it's unnecessarily complex. We generally simply write it this way, realizing that although it's not accurate, it's quite suitable. Next, we're going to look at dipole-dipole forces. So dipole-dipole forces exist between neutral polar molecules, like HCl. When polar molecules are close together in the liquid or solid state, they cohere, that is, they hold together because the partial positive end of one molecule attracts the partial negative end of an adjacent molecule. Now let's take a look at this table, and we're going to see that for substances of approximately the same size and mass, and I've chosen substances whose mass is similar, with the exception of water, well, the greater the dipole moment, or the greater the polarity in the molecules, the greater is the dipole-dipole attractions between molecules, and therefore more energy is needed to separate them. Therefore, a higher boiling point is seen. So here, fluorine, which has a pure covalent bond, has a dipole moment of 0. It's completely nonpolar. It has a very low boiling point, minus 188 Celsius. For propane, a hydrocarbon, it only has weak nonpolar bonds. It has a very small dipole moment, albeit larger than fluorine. It also has a very low boiling point. Dimethyl ether and methyl chloride have intermediate dipole moments. They still are relatively low boiling, although a little higher. And finally, we have acetaldehyde, ethanol, and water. And they contain polar bonds. They have stronger dipoles and relatively higher dipole moments. Their boiling points are relatively high. Now, propose a reason for the fact that ethanol and water have higher boiling points than acetaldehyde, even though acetaldehyde has a higher dipole moment. Can you think of a reason? Well, it's because ethanol has hydrogen bonding, in which hydrogen is bonded to oxygen, electronegative oxygen, and that creates an especially strong form of dipole-dipole attraction, which we're going to discuss on our next slide. Let's take a look at hydrogen bonding. It's an unusually strong form of dipole-dipole interaction. It exists between the hydrogen atom in a polar bond. That would be hydrogen to nitrogen, hydrogen bonded to oxygen, or hydrogen bonded to fluorine, and the electron pair on electronegative atoms such as nitrogen or oxygen or fluorine. So we're talking about this bond right here, this attraction between the hydrogen bonded to fluorine or to oxygen or to nitrogen being attracted to the non-bonded pair of electrons of fluorine or oxygen or nitrogen. So when hydrogen, electronegativity 2.1, is bonded to nitrogen or to oxygen or to fluorine, and these are the most electronegative elements, 3.0, 3.5, and 4.0, then we have large dipoles here, large dipoles between hydrogen and nitrogen, oxygen, or fluorine. The partial positive charge on the hydrogen that's bonded to nitrogen or oxygen or fluorine is greater than the positive charge on hydrogen bonded to any other element. In addition, hydrogen, nitrogen, oxygen, and fluorine, all of them are among the smallest of atoms, and the small size allows close approach of these dipoles. for maximum interatomic attraction. And so the dipole-dipole attractions between nitrogen and hydrogen, or between oxygen and hydrogen, or between hydrogen and fluorine are unusually strong dipole-dipole attractions. In a water molecule, illustrated in the center here, the highly electronegative oxygen pulls the bonding pair of electrons away from each hydrogen nucleus, each proton. This leaves the proton unshielded, and it is attracted to the lone pair of electrons on an oxygen atom in a neighboring molecule. Now, hydrogen bonding can occur only with hydrogen atoms because all other atoms have inner shell electrons, and they would shield the positive charge of the nucleus. And thus hydrogen bonding is unique to hydrogen-containing species in which hydrogen is bonded to nitrogen or oxygen or fluorine. The dipole-dipole forces between hydrogen and other nonmetals such as chlorine or sulfur are just not strong enough for it to be classed as hydrogen bonding. Let's do this short exercise. In which of the following substances is hydrogen bonding present? Draw Lewis structures of at least 2 molecules of each type and use dotted lines to draw hydrogen bonds between molecules when they are present. And the answer for the first 2 are shown. So in the case of ethane, I've drawn 2 molecules but no hydrogen bonds between them because hydrogen is not bonded to nitrogen, oxygen, or fluorine, so no hydrogen bonding is present. But in the case of methanol, this alcohol, we do have hydrogen bonded to oxygen, and so I've drawn 2 molecules and connected, if you will, or associated the hydrogen from one molecule with the oxygen of an adjacent one. There are hydrogen bonds here and here. What about acid amide? Well, we do see hydrogen bonded to nitrogen, so that would give us hydrogen bonding. If I draw an adjacent molecule, I can line up the hydrogen of one with the nitrogen's non-bonded pair of the other. There's a hydrogen bond and another one here. How about acetic acid? Well, yes, we do have an oxygen to hydrogen bond. That'll give us hydrogen bonding. Let's draw another molecule and we'll associate the hydrogen and oxygen from each of those molecules. Here are hydrogen bonds. What about ethanol? Well, sure, it's an alcohol like methanol, so the same arrangement would occur, hydrogen bonding association between oxygens and hydrogens from adjacent molecules. And finally, we have acetone, which is quite polar and miscible in water, but in this case there are no hydrogens bonded to oxygen or nitrogen or fluorine, so in fact we have no hydrogen bonding present. Electron cloud distortions and charge-induced dipoles. Even when electrons are localized to bonding or as lone pairs, they are in constant motion throughout these orbitals, and we often picture them as clouds of negative charge. So here, this xenon atom with all its electrons can be visualized as a cloud of negative charge. Now, a nearby electric field can distort an electron cloud, pulling, in this case, electron density towards a positive charge, and again here, pulling electron density towards a positive charge, or repelling electron density away from a negative charge. So when an ion's charge, like ferric ion, distorts a nearby electron cloud, an ion-induced dipole force results. This is an ion-induced dipole force of attraction. When a partial positive charge of a polar molecule distorts a nearby electron cloud, we have what's called a dipole-induced dipole force of attraction. This is a dipole-induced dipole force of attraction. The same is true at this side. A dipole induces a dipole in the xenon. Among the solubilities of the noble gases, the larger, more polarizable gases are more soluble than the smaller, less polarizable gases. For instance, xenon is about 25 times more soluble in water than is helium its smaller brother. Now, what do I mean by polarizability? Well, the ease with which a particle's electron cloud is distorted is called its polarizability, its ability to be polarized. So we can think of polarizability as a measure of the squashiness of its electron cloud, or the softness of the cloud. Now, in general, larger molecules tend to have greater polarizability. Why? Well, their valence electrons are farther away from the nucleus. They are held less tightly by the nucleus. Now, by way of periodic trends, we will note that polarizability will increase down all periods as the size increases down each period and as electronegativity decreases down each period. Similarly, the polarizability will increase from right to left across each period, again as the size increases and the electronegativity decreases. Among ions, cations are less polarizable than the parent atom, whereas anions are more polarizable than the parent atoms. Now, why is that? Well, in a cation, it's lost electrons, so it's going to hold its remaining electrons more tightly. It's positively charged. The anion has excess electrons, which will then be further from the nucleus and repelling each other. It's more polarizable. London dispersion forces. Thus far, we've studied intermolecular forces that arise from the presence of permanent ionic charges or permanent molecular dipoles. But the question arises, well, what kind of force causes nonpolar substances like xenon, iodine, carbon dioxide, etc., to condense and solidify? There must be some attractive force present even in nonpolar molecules and atoms, or they would remain gases under all conditions, even when cooled and pressurized. First proposed by Fritz London, a German physicist, weak attractive forces called London dispersion forces are created by nonpolar substances. So electrons moving within orbitals on average are symmetrical. The cloud is symmetrical on average, but at any instant in time they would be unsymmetrically distributed, as if they're momentarily bulging in any direction, creating a temporary dipole moment. So the negative end of a temporary dipole repels electrons in a nearby atom. Nearby atoms become temporarily polarized. So temporary induced dipoles align with opposite charged induced dipoles in neighboring atoms. It's almost as if the atoms join a line dance where they all step to the right, they all step to the left, they all step forward, they all step back together, kind of pulsating in sync with each other. So this is an induced dipole attraction. Now, London forces are very small, and particularly in helium, they're very weak. You see, helium must be cooled down to almost absolute zero, 4.3 Kelvin at atmospheric pressure, before it finally condenses to a liquid. That's not a very strong intermolecular force. Why is that? Well, recall that helium is a very small atom with only 2 electrons in its 1s orbital. So these electrons are held quite tightly by the nucleus, making helium not very polarizable. As a result, this charge distribution, this temporary dipole, can never be very unsymmetrical. With larger, more polarizable atoms, loosely held outer electrons undergo greater electron cloud distortions. And xenon, for example, can be cooled only to 166 Kelvin at 1 atmosphere, and then it can be condensed to liquid xenon. We're going to see here that the trends in melting points and boiling points of the noble gases and the halogens and even some of the hydrogen halides are consistent with trends in polarizability. So what do I mean by that? Well, take a look at the noble gases first. As we go from larger noble gases like xenon down to smaller noble gases, we notice that the boiling point is decreasing. And why is that? Well, we just learned that the larger noble gases would have stronger induced dipole forces of attraction, stronger London dispersion forces, because the electron cloud is more distortable. As they get smaller and smaller, they're less polarizable, therefore less induced dipole attractions, lower London dispersion forces. The same is true for the halogens. They're all nonpolar molecules. The only thing that's changing is the size. As the size gets smaller, notice how the boiling points decrease. And why is that? Well, larger molecules have greater polarizability. They're going to stick together better than smaller ones. The trend seems to hold up for the first part of the hydrogen halide series. We go from hydrogen iodide, which is the largest, hydrogen bromide a little smaller, hydrogen chloride a little smaller, and hydrogen fluoride the smallest. Notice that as we decrease in size, the boiling points are also decreasing, less polarizability. But then we have a problem here. So explain why hydrogen fluoride is an exception to the boiling point trend as seen in hydrogen halides. Well, two things are happening here. Not only is the size decreasing, but the polarity is changing. Delta En here is 0.4. Here it's 0.7. Here it is 0.9. And here it is 1.9. So even though they're getting smaller, polarizability is decreasing. They're getting more and more polar. That is, the difference electronegativity is increasing. So we have two opposing forces. Smaller molecules means less polarizable. On the other hand, polarity is increasing. And for the first part, polarizability seems to be winning because as they get smaller, the boiling points decrease. But then we get to hydrogen fluoride and the boiling point jumps up again. So in this case, the large or high polarity of hydrogen fluoride overpowers or outweighs the effect of polarizability. So small hydrogen fluoride, which is not very polarizable, has a high boiling point because it is so very polar. It has its own polarity. The last series here is an alkane series. So here we're not changing any atoms. They all have carbon and hydrogen, but we're changing the number of them. So the polarity is really not changing. They're all hydrocarbons. And the size of the atoms is not changing. We can't allude to polarizability as a reason why the boiling points are decreasing. So what would that be as we go from butane to propane to ethane to methane? Well, it's got to be simply size. So the greater the surface area, the larger the molecule, then the greater will be the force of attraction, the London dispersion forces. Smaller molecules, all else being equal, have less surface area and will hold together less. So finally, we're going to see that London forces depend not only on the size, but also the shape of molecules. So for example, we have neopentane here on the right, C5H12, which is essentially spherical, has a relatively low boiling point of 9.5 degrees Celsius. Whereas its isomer, its structural isomer, N-pentane, also C5H12, but different structural connections, is essentially cylindrical in shape and has a significantly higher boiling point, 36 degrees C. Now why is that? Well, the elongated structure of N-pentane would have more surface area contacting neighboring or adjacent N-pentane molecules as compared to neopentane, which would have less surface area. More London forces are exerted between N-pentane molecules than between neopentane molecules. Well, you've made it to the last slide. This is an overview of intermolecular forces. We can divide intermolecular forces into two kinds, those that involve ions and those that don't involve ions. Now, the ones involving ions include ion dipole attractions. For example, when an ionic compound like sodium chloride dissolves in water, a polar compound, we have an ion dipole intermolecular force of attraction. We can also have an ion that induces a dipole in a nonpolar compound, as for example when iron plus 2 ion induces a dipole in oxygen, and so the iron in hemoglobin absorbs oxygen in this fashion. It's an ion-induced dipole force. If we exclude ions from the list, then we get intermolecular forces that are called van der Waals forces. So van der Waals forces are intermolecular forces that exclude ions. There's a variety here. We looked at polar molecules only, such as sulfur dioxide, phosphorus pentachloride, and we talked about hydrogen chloride several times. Dipole forces of attraction. Now, hydrogen bonding is an especially strong force of dipole-dipole interaction. It occurs only when hydrogen is bonded to nitrogen or oxygen or fluorine, as for example in hydrogen fluoride, water, and ammonia. We also saw polar molecules inducing dipoles in nonpolar substances. So that's called a dipole-induced dipole intermolecular attraction, as you would see, say, in polar water molecule inducing a dipole in nonpolar chlorine. And that would be one of the ways by which chlorine dissolves in water. And finally, we have nonpolar molecules only, induced dipoles inducing other dipoles. It's called London dispersion forces. So, for example, in liquid bromine, what makes it a liquid? London dispersion forces. Here's phosphine, phosphorus hydride, if you will, carbon disulfide, and helium, all nonpolar substances. Induced dipole forces of attraction. Well, you made it through this long video. I've got a number of chemistry videos on my website, www.chemrat.com. Feel free to check them out. And thanks for watching.